I'd like to now introduce Manohar Paluri from Facebook. He's currently a research lead at Facebook AI Research and manages the computer vision team in the Applied Machine Learning organization. Prior to Facebook, he's worked at renowned places like Google Research, IBM Watson, Stanford Research Institute before helping co-found Facebook AI Research, directed by Dr. Jan LeCun. I'm sorry if I butchered that name, at Facebook. Manohar got his PhD from Georgia Tech. For over a decade, he's been working on various problems related to perception. He's passionate about building real-world systems that are used by billions of people that bring positive value at scale. Some of these systems are running at Facebook and already have tremendous impact in how people communicate using Facebook. Please welcome Manohar.
Thank you, everyone, and thank you for having me here. It's a Friday evening, and I'm happy that there are so many people passionate about AI and excited to hear about some of the work that we are doing at Facebook. It's a pleasure to be here. So today I was thinking of various things to talk about, and it felt kind of obvious to me that I should take a step back from computer vision, just computer vision or video, and give a bigger picture of what we are doing at Facebook in AI. So this talk is going to be technical at some places, but also going to span multiple modalities like text understanding, translation, audio, video, and vision. So, and yeah, there'll be some places where we'll go a little bit away from technical details, but hopefully it'll be useful for many people and it'll be worth your Friday evening. So there are a lot of experiences at Facebook that are powered by AI. And this should be obvious, but if not, hopefully by the end of this presentation, it will be more obvious. And one of the goals at Facebook, or the primary goal at Facebook, is we are trying to bring the world closer together. We are trying to do this by giving everyone the platform to be able to connect to what they care about, with people, with content, every day at scale. So this is our mission. Now, if you think about this and AI, we can do it in many ways. We have established Facebook AI Research, which is doing academic work, pushing the frontiers of AI without specific interest on how it is applicable to Facebook. So many of the projects in FAIR are basically pushing the frontiers of AI to push the limits of AI, not necessarily just for Facebook, but the broader community. And then I'm also part of the Applied Machine Learning organization that is trying to work on problems specific to Facebook and AI. And you will see all the projects that I'll talk about fall in both of these buckets. When we think about how AI can help, it can help in connecting content on newsfeed, helping you search about people and search about content, whether it's photos or videos. You can basically power some AI experiences on your phone. Obviously, there are some examples on Messenger that I'll talk about which use AI, and Instagram, of course, is another one. So there's just few examples where pushing the frontiers of AI can be really valuable for the company and also for the broader community. Now, hopefully this slide is not a big surprise for many people here. If you think about machine learning at scale, it's a typical machine learning cycle where you have a lot of data, and this data can be images, videos, text, people, interactions, comments, and shares, and so on and so forth. We can extract different kinds of features. We'll talk a lot about different kinds of features and networks that give you different kind of features. You do training. These training need not be deep neural networks. They can be GBDTs. They can be large-scale logistic regressions, typically neural networks these days. And then we start thinking about evaluation. And if you're start to think about inference, we are thinking about billion-plus images every day. So if you think ImageNet, every 4 minutes, there is an ImageNet at Facebook. And then, so when you put all of this together, you have to make sure that every part of that machine learning cycle is optimal so that we can move fast, we can have the state-of-the-art methods, we can push state-of-the-art, and we can actually provide experiences to 2 billion people every day. Now, when we initially started, we basically had workstations at our desk and put together GPUs and trained networks that used to take weeks and months, and we thought that was a good start, and we burnt a lot of our energy on midnight coffees, and the coffee bill was going up. So we basically said, okay, let's do this a bit different. Let's build the machine learning platform for Facebook. What does that mean? So anybody at Facebook can now use someone else's machine learning workflow, clone it, and run it on their data. This is very, very valuable, and This increased the productivity, reusability, and made whole of machine learning efficient and comprehensive. What do I mean by that? So right now, every ML engineer at Facebook, whether they are a non-AI expert or an AI expert, can actually go and use this machine learning platform instead of worrying about the finer grained details on the scripts or visualization or data preparation and so on and so forth. And there are every 1 in 4 person at Facebook actually uses this machine learning platform or the AI platform. And there are many, many workflows every day, and we train 2.2 million models every month. So the scale is massive. Some of these examples that we train look at 2 trillion examples. Like I said, there are multi-million models every month that we train. So it gives the first step of I can iterate fast on machine learning models. Then we can get to the research aspect. So what is the research? If you put all of these together, whether it's computer vision or natural language understanding or translation, what we are trying to do is content understanding at the root. And how did Facebook start? So Facebook started with a lot of people connecting with each other. And they started communicating with each other using text. But then they started going towards using photos, sharing photos. And now we have a lot of video content. If we think about building the AI foundation blocks for each product experience, we'll not be able to scale. So what we did is we took this social graph and we basically made it semantic. So every content now is understood by the AI algorithms. So we have image models, we have video models, we have text models that add artificial nodes, whether what is this post about, what is the commentary about, what is this photo about, and what is the video about. And that signals can then be used for applications like Facebook for Blind, Newsfeed, photo search, 40, 50 different applications. So this is one way we scale. If you think about 1 billion images processed every day, we can't have more than 1 deep net or 2 deep net or 3 deep nets processing them. It's going to be a tremendous infrastructure cost. So that's exactly what I want to talk today. How do we do this at scale in a state-of-the-art manner? Not only just for people understanding, for text understanding, for audio, video understanding, and for translations. So that's what I want to get out today. So let's start with vision. So we built this platform called Lumos on top of the machine learning platform. What does Lumos do? It runs on billions of images every day. We have more than 200 visual models, and these models are trained with more than hundreds of millions of examples. One of the nicest things or the best advantages that we have is the state-of-the-art models are deep residual networks. So what is so unique about deep residual networks and these CNNs? One of the things that's unique about it is you can train it on a task, but its hierarchical representation, so you can actually have multiple representations in the deep net. But you have a new task, typically we could train another deep neural network for the second task. But we don't do that. We have learned that because of this hierarchical representation, I could possibly use some of the existing features from various layers to train for my task. And these auxiliary tasks, when it's closer to the original task, then the features are pretty good. But when it's not, then obviously you might have to go deeper and train some other modules on top of the existing residual network modules to basically get accuracy. So essentially what we're trying to do is finding this trade-off between compute and accuracy. And that's exactly what happens every day when engineers in Facebook go to Lumos and start building models for their scenarios. And we as a computer vision team, we are a small team. We don't know all the scenarios that you will be using these features for. So think of the core network, the trunk, as a representation learning engine instead of a deep neural network that's just doing classification. So what happens today is we have this core trunk that is trained on many, many, many tasks, and then you can use the features at various levels, at various hierarchies to basically get the job done where you're actually reusing the compute at different scales. Now this is important because most of the compute in the deep residual network happens in the lower level layers. And by reusing it, I'm actually saving a lot of infrastructure cost. And we are now putting the decision of how to fork this network into the hands of the product groups and the engineers who know the different trade-off between 1% accuracy loss versus 10,000 more machines. This is something that we as a computer vision team wouldn't know. But they, as ads ranking or feed ranking or photo search, would evaluate the cost, and Lumos gives them this capability. So that's exactly what Lumos, and as part of Lumos, you can actually do a bunch of things, not just reuse the features from existing networks. You can actually collect training data. I'll show you a couple of examples. This is really critical. As the previous presentation pointed out, these models are data hungry. But the nice thing is, because they're pre-trained, you don't need as much data for adding new concepts. You can get away with very few training examples and a lot of random negative examples. So here is an example where you want to train a model, you search for a keyword, and here you're searching for fireworks. Let's say it's just July 3rd and we want to have a classifier for fireworks. You can search for it and you can say, pick from the previous day's Instagram data, hashtag firework photos, 10,000 of them, or in this case, 50 of them. And then when you do that, we have clustering mechanisms where you have annotation tools. We have clustered them using the existing feature representation, and instead of annotating one image at a time, you can start annotating clusters at a time. So you have expedited the process of annotation, which is a big bottleneck to train some of these models. So once you can browse through these clusters, you can basically say, most of this cluster is positive, most of this cluster is negative. And it's okay to have noise in these clusters, because the noise is always going to be random, but the signal is going to be very characteristic. So this is very critical. So even if you have 10%, 20%, 30% noise, you can actually train models and then do active learning. That's one of the advantages of Lumos. So here you're creating a new, let me go back. So here is an example where someone uploaded a photo and you immediately in real time, so when you upload a photo on Facebook, within the first 2 seconds, you basically get all of these scores, and the system, like I said, the social graph is populated with all of these concepts. If I want to go back and show you one particular flow to basically highlight how easy it is to train a new visual model. It's much less of research and much more of engineering now. Because we have these embeddings. Can we go 2 slides back, please? Okay, yeah. So you just say, I want to create a new model for horseback riding. So as I said, you go and add training examples. You search for data on Facebook or Instagram using some keywords or hashtags. You just say horseback or horseback riding. Say how many examples you want. It populates the examples. Some of these clusters are good, some of these clusters are not good. And you think that one of the clusters is good, and you can even go and correct a couple of examples. It's a pony, not a horse, and maybe another example. Right? You don't need to do it because these models are pretty resilient to noise. And then you're happy with the training data that you have. You save the annotations. You train the model, and in training the model, you can observe that they're existing. So there's a visual cortex model that was trained on something. So this is the core trunk, a residual network that you can use to train, and you get precision recall on the data set that you have, and you can even click on the high scoring examples and the low scoring examples and see what your model is doing. Here you're clicking on the high scoring examples on live preview, so it simulates production, and it shows you what are the high scoring examples for horseback riding. You can see now this model has never been trained on horseback riding, right? So what it's doing is it's picking up examples with people and horses, but not people on horses. So what you can now do is you can go back and say, here are examples which are negatives, and then you can retrain the model. So you're now doing this active learning loop. You've reduced the problem of horseback riding classifier into a few-minute job and pushing it to production. So I just wanted to highlight how easy it is because of these tools and because of how good the representations are in generalizing for new concepts. So this is the example that I talked about. So the model knows about scenes, about objects, about actions, about relationships, and also some fine-grained recognition. And as I said, we have one ImageNet every 5 minutes. These billions of photos go through these classifiers, and you can look at the high-scoring classifiers and easily remove the false positives. There are some, you can have annotators do this, or you can do it in some weakly supervised learning way, and so on and so forth. We did this, we shipped it for accessibility feature. So there are roughly 100,000 to 500,000 people who are blind, visually impaired, who use Facebook every day. When they browse Facebook, they actually get these notifications. This image may contain these many people doing this activity. It contains a dog, etc., etc. So this is running in production. This is running live and used by hundreds of thousands of people every day. And it's very rich. It tells you about the number of people, what activities they're doing, and so on and so forth. Now, that's a little bit of a teaser for vision. We'll come back to vision again in the concept relevant to video. So let's take a step towards text understanding. So Facebook has a lot of text. There are almost 2 billion people every day who are interacting with each other in various contexts. So we want to understand this text and build experiences around that. Here is an example where we had NIPS last year in Barcelona, and one of my friends is mentioning that he's going to Barcelona and he wants to watch the El Clasico match. It immediately realizes the intent and it starts searching for people who are basically who can give the intent of the post that says that I'm going to Barcelona, I'm looking for recommendations. So whatever you comment on basically puts the pin on a map. Now you know where your friends are recommending you to go. This is because we understand that this post is about asking for recommendations and the replies are going to be about entities that people are recommending. So it's a very simple tweak, but that helps you in quickly connecting with people and their experiences and makes your job easy to explore a new city. You can take this a step further. You can basically say, I want to buy tickets. Somebody's saying here in Spanish that they want to buy tickets for El Clasico and they're willing to pay $450. So you look at the text and it's a multilingual, so we have multilingual representations. So we have convolution neural networks that map from one language to another language. We have 1,400 such neural networks with all 140 pairs of languages. And basically, it looks at this and it goes to the multilingual representation and it connects to someone who is actually selling tickets for El Clasico. So here there are three things that are happening. One, we are doing real-time translation. Second, we are looking at the intent that someone wants to buy the tickets. And third, we are actually looking at the intent that someone wants to sell the tickets and connecting them in real time. So this is based purely on convolution networks and the translation technology that I'll talk about in a little bit. So I got the tickets, happy, my friend is happy. And you can see that he is basically writing the translation, writing the text in Spanish, but it's doing real-time translation, and you can rate the translation. And this translation is now powered using convolutional neural networks instead of RNNs. So why is that important? Let me tell you a little bit about how RNNs are going to be are not necessarily good for translation compared to CNNs. And the future is more in the CNNs. This is work coming out of Facebook AI research. So if you typically take a sentence, this sentence is embedded using a one-hot vector representation, and it goes through an LSTM or an RNN for temporal modeling. And then you have a final MLP that is either giving you classification or intent or slot filling and many other tasks in text. But it cannot be parallelized. In an RNN, you have to go through one iteration after another, and you cannot parallelize it. One of the advantages of CNN is you can actually parallelize it, because you take the same embedding and you can pass through the CNN all at the same time, and when you get the next layer output, you can keep doing this, whatever is the hierarchy. And not only that, depending on how deep the CNN is, the layers have a bigger aperture to what the words are talking about, which is not easy in an RNN if the sentence is very, very long. So there are very many advantages of using CNN for text understanding, and this is what gave us state of the art. But even training the CNNs that are very deep take a long time and are slow. It takes days to train this. So what we did is we developed this thing called fast text, and it's actually available on GitHub that anyone can use. The simple idea here was to, instead of using the text as one-hot representation, we basically do some limited feature engineering. We know that n-grams or bigrams are actually useful in NLP. So what we do is, instead of sending the one-hot representation of the original words, we just compute bigrams, and the input to this network is a bigram. And the network, believe it or not, is only one layer deep. And there's only one hidden layer. This is a classical neural network where you can approximate everything in one layer, right, with exponential number of nodes. And then you have the output. The advantage, there is some novelty in the loss function. I don't want to get into the details. It's all in the fast text paper. But we can train on millions of examples in less than 5 minutes. So if you want to actually now train an intent classifier for text, then you can actually put all of these examples, and within 5 minutes, you have a network, a one hidden layer network that is state of the art. This is fast text. one of the problems that we have is not just intent recognition, but actually entity recognition. So what I mean by that, people would never enumerate the entities when they talk about text, right? So you take the CNN models, but for every word, we have an MLP at the top, which actually classifies what entity it is. The example of this is, let's say I just made a post, I am watching Barcelona and Real. I'm not going to enumerate Real Madrid. So the networks can then actually take each of this word and map it to existing entities, and Facebook can then know that he's talking about FC Barcelona, he's talking about Real Madrid CF. And this way, we can actually do connection of the events or groups or other connections. That is not trivial, because you're just writing some text, and mapping this text to entities is critical. So this is an example where we had translation running based on the phrase-based system. So older methods on translation are phrase-based. And as you can see, it gets all the words right in translation, but the end meaning is not right, because it doesn't look at the full sentence. The CNN models, on the other hand, not only get the words right, but also get the meaning right. And the accuracy jump between a CNN and a phrase-based system is significant. So most of the translation models running at Facebook today are CNN-based. One of the things that I'm personally excited about is social good. So accessibility was one project that came out of our group, where we were actually materialistically helping visually blind, visually impaired people. Another example that we recently launched in India was around blood donation. So today, there are 1.5 billion people in India, and many people actually voluntarily register that they want to donate blood. So we have some notion of what blood type people are and so on. But when you go and make a post at Facebook that I'm looking for blood donation, basically the post is parsed using our fast text models, and it understands the blood group. It understands that this post is about blood donation request, and it immediately notifies the people who are actually willing to donate blood. And this is saving lives in many, many ways. So this is a very simple example of how you can take fast text or existing models in that ML platform that I was talking about and create new experiences for various scenarios. Let's take another example of Messenger. In Messenger, let's say you're having a conversation. You can start seeing that the underlying AI understands what is the intent, what is the conversation about. So here they're talking about dinner. You can, in Messenger, look at nearby restaurants. It's using the location. You can look at the menu. You can basically select the menu, push it to the cart. The other person, your friend, will look at the cart, and you can ask, do you want to check out? They say yes. You use Messenger. You basically look at the amount. You can use Messenger Pay. You confirm the dinner is going to be there. You can have a nice dinner together. So all of this purely from NLP techniques in Messenger, where you're having real-time conversation. It's understanding in real time what the intent is, and you don't have to go out of your screen and get the stuff done and care about much more about your interaction with your friend, not about anything else. Now, we talked about translation. We talked about text. I haven't spoken a lot about speech and audio. There's a lot of cool work happening in that sense too, in that domain too. And then there's a bunch of work we talked about in images. Video is the next big challenge. It brings all of these together. Because in video, especially in Facebook video, it's about people. People communicating with the rest of the world, people communicating with their friends. There, I need to understand what they're speaking, which is speech recognition and audio event analysis. I need to understand the vision components. Once I know the transcriptions, I need to understand what the conversation is about. So in video understanding, we have built some state-of-the-art networks. I'll explain them in a little bit, where we put together all of the techniques in one place. So here, you will see an example where we have on-device, real-time. Your mobile is basically doing this right now. It's looking for people, doing segmentation of people, and doing pose estimation of the people. So you understand now what people are doing in video. And then you can combine that with face detection, face recognition. You can combine that with speech recognition, real-time translation, pose estimation, and then you have a crystal clear understanding of what exactly is happening in video. When are the events starting? When are the events ending? When are people coming in? When are people going out? What are they doing? What kind of activities are performed and so on and so forth. And then you can do a much better job in newsfeed ranking or search or create new experiences around this. So this is something that we can take a step further. As I said, if you think about video embeddings, it's the same, right? We can actually, here is an example where you can train a model for video classifiers, where you can actually combine vision components, text components, audio components together in one framework and train a model for video classification. So this is also part of Lumos now, where you can combine all of these features, as you can see in the demo, where here you're combining text and vision together. We don't combine audio here, I guess. And then you can see in real time all of the videos that are being processed by, that are being uploaded to Facebook or shared. You can do real-time classification of these videos for scenes, objects, and actions. So the models that are running here are more or less frame-based models, but there's a significant jump in accuracy that you can get from going from frame-based models to video models. There is a lot of work in the community on motion temporal modeling, basically. You can have CNNs with RNNs on the top. We have published a bunch of work. Our model was C3D, where we did 3D convnets, where from bottom up, we basically do spatiotemporal convolutions. There'll be a paper out, I can tell you, because CVPR deadline is done. So there'll be a paper out very soon where we actually factor the convolutions. So if you have these 3D convnets, you have n-cube parameters that you need to learn. And that is very expensive. So what we do is we basically take that 3D convnet and factor every convolution layer, 3D convolution layer, to 2D and 1D. By this, you can actually save a lot of capacity. So you have n square plus n parameters instead of n cube, right? So that gives state-of-the-art results on activity recognition and datasets like kinetics, datasets like Sports 1 million, which are the large-scale video datasets. Here is an example where we use multiple signals to train for fireworks, and you can see, again in Lumos, that you can have video classification for fireworks. So it's very simple to go from images to video once you have those embeddings, once you have those representation learning machines. Mascar CNN was something that came out of FAIR. It won the Best Paper Award recently. So this is instance-level segmentation network. So the demo that you saw is basically one network instead of many networks. So the frames of video are passed through Mascar CNN, and in Mascar CNN there is a trunk that actually tells you what are the region proposals, where I should be doing detection, and those region proposals then go to the detection trunk, go to the segmentation trunk, go to the pose estimation trunk. So as part of the output then, when you go from a single image, you can get segmentation, detection, and classification in one network. So you don't have to run multiple models. It can also do pose estimation, which is critical to understand humans in images and video. And these are not ground truth outputs. These are actually outputs from Mascar CNN, which are pretty impressive. You can take this Mascar CNN as is and apply it on video frames, and you get really compelling results, even in hard scenarios. So it's doing pose estimation and segmentation in some really tough scenarios. This is another example where the person is doing acrobatics. So we are not doing any temporal tracking or any temporal model. What we are doing is taking state-of-the-art image network and applying it on every frame and pasting the output. It's pretty impressive that the segmentation is so coherent. We also won the post-track challenge. There were 3 challenges in post-track where you're doing pose estimation, but over time in video with multiple people. So here we took Mascar CNN, we passed each frame to get the pose, and then we do Hungarian matching for each joint, and that gives you state-of-the-art for post-tracking in video. Here are some really compelling examples where there is occlusion with multiple people moving, and the pose estimation between people is very accurate. There is obviously, you always want to show where the system fails, otherwise our jobs are not intact, right? So here is an example where it's really, really difficult to do pose estimation. So we are not done yet. As much as the results are impressive, we can still go back and work on Friday nights. We took these Mascar CNN models and we did quantization of the weights. We pruned the network. This is a paper that we submitted in ICLR. It's called DSD, dense, sparse, dense training. So you take this dense model, you sparsify the connections, and then you make it dense again, which is a really good regularization to save the weights. And then you can run this on your iPhone at 10 frames per second. And the size of the model is less than 1 megabyte. So we don't need cloud GPUs to start understanding videos. Obviously, there is some loss in accuracy as you see, but it works really well, irrespective of all the compression and other aggressive things that we did. So if you think about training these deep nets, it is insane that we have to build this architecture and then wait for 3 days or 2 days or 7 days, depending on what you're training, to get back the result. It is actually inhibiting us from innovating on the real deal, which is how do we build these architectures for scalable data sets for generalizable problems. So one of the things that we did is we pushed to the extreme on data parallelism, where we have batch sizes of more than 30,000. And we use 256 GPUs to train ImageNet in 1 hour. But when we do this, the convergence is not the same as with 1 GPU. It's understandable because you're doing gradient approximation, you're doing SGD. Right? So there is all the details of this are published. The code is there. It's ImageNet in 1 hour work. This actually helped us innovate on the architectures that I was talking about, both in the Mascar CNN image world and in the ResNets, 3D ConNets for ResNets for video world. So we are able to train, I don't know how many of you know the video data sets here. UCF 101 is a reasonably famous data set. Sports 1 million is another data set that's large. We are able to train Sports 1 million in 1 day. So now we can actually start asking fundamental questions. What are good video architectures for various video problems? Yes, we can ask that. We can use all these nice residual networks and for video, but at least in video, I'm not convinced that we have good data sets, and the tasks that we are solving are essentially the perfect ones. For example, you could do Sports 1 million, which has 487 sports, but sport classification is just one minor problem. If you really want to do video understanding, you might have to go beyond that. And one of the fundamental problems that we are noticing with video datasets is you can just get away with frame-based models. You don't necessarily have to do motion modeling for the tasks. So look at this example from UCF 101. You don't need to see the video to basically say this is baby crawling or someone is kayaking or this is bowling, right? So we have been asking what data sets should we create and work with the rest of the community to push the modeling for video and where frame-based models actually fail. So we have 2 answers for that. And I'm super excited to basically say this is the first time where we are taking these data sets and making it available for public so you can train on this data. So one of this data set is SOA. I'll tell you in a little bit what that is. And the other one is generic motions. And both will be open source next year. So SOA, it stands for scenes, objects, and actions. When we are thinking about video understanding, it's not action recognition. It is not just about scene understanding in video. It's not about what objects occur in video. It's the combination of all these 3. So when we are thinking about building models for video, we should be thinking about solving all these problems together and see where image models do well and where video models do well. In this particular data set, it's a large scale, fully supervised data set. So we spent a significant amount of resources to annotate small video clips. We didn't want the academic community and the rest of the community to not participate because of the scale. So we basically took untrimmed videos and took parts of it and annotated only those videos. It's a multi-label, multitask problem. As I said, your model has to predict the scenes, predict the objects, and predict the actions. These were annotated by professional raters, not Amazon Turk members, so the accuracy of labels is very, very high. And we're super happy that we are actually going to put the audio labels as well. So this is a truly multi-model understanding data set that we can test our models on. This is just an example of an annotator and a reviewer basically creating the labels. So they look at this short clip of video and they basically go and add objects. It's free form. We don't give a drop down. So whatever objects they feel should be there, they add that. Whatever actions are occurring in that short video, they add them. And whatever scenes, if there is any scene change, they add those too. It's free form and there are professional raters doing this. And obviously when you do this at this scale, you have a long tail, so the green I believe is scenes, red is objects, blue is objects, red is actions. I have to verify. But what I wanted to show here is even though it's long tail, you have roughly 1,000 examples for every object. You have roughly 1,000 examples for every scene, and you have roughly 1,000 examples for every action in the long tail. And the ones that are frequently occurring, you have tens of thousands. That was SOA, and we have done a bunch of work on architectures for SOA, and our finding has been, so there are many state-of-the-art networks in video, whether it's I3D, which is using optical flow and RGB as two streams. It could be LSTM on top of a CNN, like a ResNet, or it could be the 3D ConvNets work that we have done, where we took C3D and we basically evolved it into Res3D. So you have 3D ConvNets with residual connections. But the state-of-the-art numbers on SOA are basically from factored 3D convolutions. So we are calling it Res 2 plus 1D. So every 3D layer now is factored into 2D plus 1D. And that gives you the most efficient capacity usage, as well as trains faster and gives you better accuracy. So all of this will be in the archive paper that we'll put out. This is the second data set that I'm excited about. It's a generic motions data set. So why is this data set important? It's a little bit orthogonal to SOA, but here what we are trying to think about is when we are thinking about motion modeling, we should decouple it from objects. So let's take a couple of examples. So that's falling or sliding. We don't need to see a 1-hour video or 10,000 examples of falling. If we can abstract it out, irrespective of whether it's a cat falling or a panda falling or an elephant falling, that is what we want to learn when we are thinking about the action falling. And the same, jumping. Yes, we will not see cars jumping, but we should still be able to explain cars jumping, because jumping is not associated to just humans or animals. Jumping is an abstract concept that anything can perform virtually, right, in a synthetic data set. So these are all GIFs where we have annotated these GIFs into these 20 actions. We just picked 20 because those are the ones that really needed motion modeling. This is basically sliding. And then this is sliding and falling, right? So it's a very small video with multiple actions, and now you're forcing the models that, yeah, it is funny. I'll give you guys time. So what's happening here is if you just look at one frame, you cannot predict sliding, you cannot predict falling. You have to look at the whole GIF. That's the key value of this data set, where we're going to push any of the models that we're doing, that we have to understand motion. And there are some unique aspects. It's focused on motion. It's generic to different objects. So you will think of action, and different objects will be performing that action. They are GIFs, so very, very small. You don't need computational resources for building state-of-the-art models on this. It's a multi-level problem. You saw cat sliding and falling. And it is fully supervised. So there's no noise. There is no machine learning, previous machine learning model noise or biases. Most of the work that I talked about is open sourced. It can be used by all of you guys. They're on it's on GitHub. The models are there. The code is there. And this is something that we believe in fundamentally, to work with the community when we are pushing the frontiers of AI. For me, I have been at Facebook for over 5 years now, and the thing that I'm most excited about is between the curve of real research and development, where you're pushing the frontiers, and product use cases. And when you're in between these, you traverse that spectrum every day of seeing core technology, building core technology, and having fun with it. And then you go and see 2 billion people using what you're building, and then giving you feedback in one way or another. That's an exciting time for us in the AI community, and specifically for me and my group at Facebook. With that, I'm open to questions. Thank you.
Question. Okay, excellent talk. I'm excited, okay? The question here is this, okay? You folks have power, can either literally change the face of the planet of Earth, okay? Or ignite a revolution, kind of like a wildfire. Okay, so we all know that the last election in America has been influenced, let's use that word, by a foreign government. So today, as Mark Zuckerberg mentioned, that he would like to see this type of unpleasant situation to be more difficult, meaning raise the barrier. I can see that you might have the technology to do that, but on the other hand, is how do you use the technology to raise the barrier for that kind of action? I mean, one very brutal example is, what if people wanted to reignite the independence move in what's called Catalonia in Spain? So how would you be able to stop people using Facebook as a platform and a vehicle to do that?
So this is not my expertise, of course, right? So I can only comment on the things that I know, especially from the AI technology side.
Yeah.
We really believe in not making decisions for the people, but rather giving the platform and the ability to communicate and express their opinion. As long as it's respectful, it is not hurting other people, right? So there are policies in place that help us actually keep it healthy, keep the conversation healthy, connect it to the right people. So some of the things that we actually publicly talked about, and I'm happy to share, is if you're thinking about a news article, right? If you have friends who believe in one side of the story, not the other side, then typically you start getting one-side information, right? So we are actually investing in AI technologies that can actually expose you to both sides, right? And you can then make a decision which side is correct, which side is what you believe in, right? So this will take a tremendous amount of AI technology, and that is what I feel we need to bring to the table as technologists, right? Beyond that, Facebook is basically a platform that can be used in many, many ways, and if it is actually being used in bad ways, we will enforce policies. We are working very hard in building the technology to move fast, and some of the things that I talked about Lumos or the ML platforms are essentially for that, where the adversaries on the other side are moving faster than us, so we build the tools so that we can be faster than them. And it's always, the adversarial ML game is always a tough game.
Oh, yeah.
And you can only defeat it by having the right machines and the state-of-the-art technology.
Yeah. Thank you.
Thank you.
Okay, yes, thank you very much for that talk. It was fascinating. That's some wonderful work you're doing there. I have a question that relates a little bit to the last one, in fact, and on the deployment of AI on a large scale such as you do in Facebook, and it relates particularly to machine translation. Here's something that happened about a month ago. I have a friend who is Finnish. She's fluent in Finnish, and she's fluent in English. She noticed that she was getting some very odd responses to some posts she made on Facebook in Finnish. And after trying to figure out why, she eventually checked what the machine translation was. And she found that the machine translation into English was putting swear words all over the place in the English that were absent from the Finnish. And worse, when you talk about Facebook maintaining a healthy environment, that the automated emails about proper content were complaining that her content was not proper when it was Facebook's translation that was putting the improper content in there. So my questions are, when you have AI deployed on a large scale like that, how do you detect when one of your AIs has started to generate bad predictions? How do you correct it? And what ethical responsibility does a company deploying that AI have in maintaining the integrity of its predictions?
Yeah, this is a great question, and this is a challenging one, not just in the translation domain, but even in the Facebook for Blind initiative, right? So one of the things that we noticed is, what if we got one of the labels wrong? Even if you're 99.99999% correct, if you're processing 1 billion, you are basically going to make 1,000 mistakes, which is not good, right? So there are two ways to do it, right? One, you never ship the technology. And then I would never understand, you would never understand, or that person would never understand the Finnish words, 99% of which are correct, and this 1% scenario where it's not. And the 1% scenario where it's not, we have ways where you can give the feedback, where we actually try our best to fix that loop and make the models better. That's where the active learning comes in. So the alternate is complete closure of communication. And in Facebook, we have 2 billion plus people and thousands of languages. So there is, basically, you would not have conversations beyond political barriers. You would not have conversations among multilinguists, multilingual friendships, and so on. So while it's challenging, while these models are not perfect, I do believe they're much better than phrase-based systems, or much better than not having a conversation where we have on Facebook people who start a Chinese conversation and the rest of the races, people from other countries chime in because of this auto-translation. But I agree with you. There are places where you can improve this quite a bit, and we are working on that. That's one of the things that's exciting for us.
Very nice presentation. I really enjoyed it. First question is, when is the SOA data going to be outsourced? I'm really looking forward to playing with it. And two, in terms of text classification, chatbots are the in thing now. Everybody is all over the place, but they are mostly using retrieval method. And the problem is because of semantics context. So if you have done anything in that research, if you can speak to it.
Yeah, absolutely. SOA, our current deadline is January. The team is working really, really hard. We probably won't have our Christmas because of that. So, because we do want to put it out there, and we want the rest of the community to work on video. I think it's time that we push the frontier on video the way we have on images. So we are definitely working really hard, and end of January is what we're aiming for. On the second question, there are two efforts that come to my mind. There might be more than these two, Com AI and Parl AI. These are things that we talked publicly. These are efforts in Facebook AI research. These are two frameworks where you can go beyond intent recognition, slot filling, or retrieval methods and go deeper. So one of the things that we are thinking about is how do we embed words, sentences, paragraphs, a book in a uniform way. Nobody knows how to do this, right? So Com AI and Parl AI are two efforts in the language space where we are thinking of dialogue, where we are thinking of embedding text at various scales. And the other effort that I think will be interesting, or at least I should mention, is the M effort that I just showed you. So M basically is we are having humans help, and then the machine look at how the humans help so that we can start automating. And that's a very, very difficult problem because we are in the semantics, right? So we have some automation of it, but it's early work. I feel people have a notion that vision is working better than language, and people might disagree with me, but I think vision is catching up to language. If you think about the outputs of vision, they are entities at most. They are nouns. They are not even relationships. Whereas the place where language is in the semantics. So we are actually exposing the limitations of language because we are thinking vision is working well, but it's the other way around. We'll start soon realizing that in vision we need to do a lot more high-level tasks than classification, detection, and segmentation.
So maybe a follow-up to that, a technical question. You mentioned convolutional neural networks work best in certain contexts, including language, n-grams, and so forth. Now, with any type of neural networks, there's always this interpretational challenge.
Yeah.
You train the network, certain weights work well. How do you attach, this is 0.0115 and this is minus whatever, okay, inhibitory effect versus excitatory using biological paradigm, but like beyond that, how do you connect a well-trained network of any variety to semantics, to meaning? Any insights from recent R&D at Facebook in that?
Yeah, so there are two efforts, one that's already published, one that we just submitted to CVPR and will be on archive. The one that's already published is GradCam, where you backpropagate the gradients and you see which pixels amount to the decision. So you can actually get heat maps, a Gaussian heat map or some sort of heat map of which pixels in the image give you that confidence. And if you block that, the confidence goes down and up, right? And the same for language. Which words give you that this is politics or what topic this sentence is and so on and so forth. So you can actually use GradCam irrespective of what type of network it is as long as you can backpropagate the gradients. So that's one that's already published. The second one that I think is more interesting is going a step further than diagnosing, right? So diagnostics is one way. It's just actually giving you more confidence on the predictions. So what we did as a step further is to understand how each neuron in the network, what is it learning in a data-centric way and putting the right neurons in a modular fashion. So this is early work. I want to caveat it that way, but I think it's promising to basically start thinking of these neural networks in the more classical computer vision style, where I'm actually making sure that I understand what each modules are doing at various levels, and I understand how each neuron is firing and what neurons I want for my task. So
great, thank you. And maybe to follow up offline, is your group open to academic researchers getting involved in some, especially of this latter effort? Maybe
Absolutely. We have a visiting faculty, we have postdocs, we have research interns, and we have grants that we give out. So we are definitely interested in collaborating with academia.
All right. Can we give?
Thank you so much for spending your Friday evening.
Yeah, I'd like to ask you just to stay for a few more moments. Okay, thank you very much. So I'd like to ask you just, I mean, it's already late and many people already left. So on behalf of IEEE Silicon Valley, I'd like to thank you for attending the seminar and all your support. I just wanted to mention I think a couple of more comments. So one I forgot to mention yesterday during the opening remarks is that please support the IEEE community. If you are not a member, please become a member, join IEEE, and it's just a matter of awareness. So you could just join the society and also IEEE and also get engaged with the local activities. And second, I'd like to thank our volunteers and the staff who make this event possible. So we have a lot of so we had 20 to 30, 20-ish volunteers that helped us to manage the event and get the logistics going. And as you know, IEEE is nonprofit, so everybody is volunteering, contributing to our technical community. And the last one, yeah, I just wanted to ask you to basically recycle your badges, both your badges, to the basket outside. And with that, thank you very much. Yeah, sure. Yeah, grab a bottle of water so we have a lot of leftovers. Thank you very much. And also, we'll probably have this event organized again next year. So please come to us if you have any comments or feedback. Ask for speakers or organizer. Thank you very much, and have a great weekend.